Trying to make it to the end of the day. Ophir is going to give the last talk.
So hi everyone, can you hear me? Okay, so this is joint work with Michal Feldman and Aviad Rubinstein. We're going to talk about revenue. So the settings that we're going to talk about are those of many buyers and many items, and we are going to try to maximize revenue using truthful mechanisms. And specifically, if we look at the single item case, we are going to look at, also in the many items case later, we're going to look at I.I.D buyers, which means that the valuation of each buyer is drawn from the same distribution. So for those who are not sure, this is a watermelon, and the valuation of the value of the watermelon for each buyer is drawn from the same distribution independently. So for this setting, Meyerson in 81 showed that the optimal mechanism is something, and it is dependent on the distribution F. And then later, Buell and Klemperer showed that actually the second price auction with one more buyer is a mechanism that is truthful and generates more revenue, or at least as much revenue, and it is also independent of the distribution under a regularity condition. So this is the situation for a single item. And for many items, some questions are still unresolved. For example, the optimal mechanism in general is still largely unknown. It's still an open question, which is probably not going to be solved in a closed form. And also the questions of which auctions with how many more buyers would generate just as much revenue is still largely unknown, and this is the main point of this talk. So we're going to talk about heterogeneous items, that means different items that come from different distributions, and I.I.D buyers. Also, we're going to assume independence in the sense that each item has a different distribution, and the value of each item is drawn independently from this distribution for each buyer. And moreover, the buyers are going to have additive valuations, which means the value of a bundle is just the sum of the values of each item separately. So this setting has been studied thoroughly in the past, and we're going to look at this setting as well. And what we know is that for the single item, there is this mechanism that Meyerson described, which is both optimal, deterministic, and it has a somewhat simple description. And for the many items case, the situation is way different. For example, the optimal mechanism may be necessarily randomized. There are some non-monotonicity properties. There are complexity properties. For example, this menu size that is shown to be infinite in some cases. The optimal mechanism in the setting can also be hard to find in a computational sense. And in general, we're not hoping to find a closed form for the optimal mechanism. So the simple versus optimal line of work is asking, okay, so if this is the case, how much revenue can we guarantee using simple mechanisms compared to the optimal revenue that we can't achieve anyway? And in this line of work, many papers eventually culminate to the concept that a constant fraction is possible using simple mechanisms. For example, in the additive case, if we either sell items separately or in a VCG manner with entry fees, then in this additive setting, we can get a constant approximation to the optimal revenue, and deciding which of the mechanisms depends on the distributions. Another earlier result by Tsai and Huang showed that for for distributions that satisfy an MHR condition, you can also use simple mechanisms and get not just a constant fraction, but a 99% of the optimal revenue using simple mechanisms. And they strongly rely on the MHR condition. Another question that was asked, which is similar to the Buell-Klemperer result, is how much more competition, how many more buyers do we need to bring to the mechanism for simple mechanisms to exceed the optimal revenue that we said we cannot achieve in the general setting? So Buell and Klemperer showed that one more buyer is enough when there is just one item and the buyers are coming from the same population. Roughgarden, Talgum Cohen, and Yan showed result for unit demand buyers, and in a paper from last year, we showed that if we sell items in a VCG manner to a number of buyers that is a constant times the original number of buyers plus the original number of items, to buyers that are coming from a regular distribution, then we can exceed the optimal revenue. So On the one side, we have approximation. We can get a constant approximation with no extra competition. On the other side, if we increase the number of buyers by an additional constant times the number of buyers and number of items, we can exceed the optimal revenue. And in this paper, we ask the following question. What is the percent of the optimal revenue that we should aim for? So on the 100% case, a linear increase in competition suffices, but this is somewhat maybe too much to ask. In case there are many buyers or in case there are many items, a linear increase might be too much, too greedy to want. On the other side of things, we can get a constant approximation with no extra competition. However, losing 80-something% of the revenue might seem a bit prohibitive. And what our opinion is that shooting for the 99% instead of the 100 can be the most interesting question, specifically because we can show that we need much less competition compared to the 100% case, and specifically an exponential improvement from linear to logarithmic, sometimes a constant, and sometimes no extra competition at all. So any questions so far? OK. So to specify our results in this paper, so for n buyers coming from the same population, from I.I.D. buyers, if the number of items is at least is larger than the number of buyers, we can get 99% of the revenue by selling items separately and optimally to a number of buyers that is a constant times the original times log of the number of items. So for example, when the number of items is very large and the number of buyers is reasonably small, then we get an exponential improvement to the previous result at a loss of 1% revenue. If the number of buyers is larger than the number of items substantially, the previous result says that we need to increase the number of buyers. We need to multiply the number of buyers by a constant, but what we actually show that when the number of buyers is large in the first place, then no extra competition is required. Specifically, if the number of buyers is sufficiently large, then selling items separately is 99% the right thing to do. So these results are achieved by using the core tail decomposition that was presented by Li and Yao in 2013. We used the technique to create new bounds, and I will talk a little bit more about that later. And we also have a tightness result that essentially what it says that the first result, the n times log m result, is essentially tight up to constant factors. We have a few more results for the case of one buyer. So if we have just one buyer, then we know that logarithmic increase in the number of items suffices to get 99% revenue. But actually, if we choose to either sell items separately or sell the grand bundle to a constant number of buyers, then we can get 99% of the revenue. And those who are familiar with the literature, this compares to the Babayev et al. Result from 2014. But actually, this result implies the other one with worse constants, but not the other way around. And we used previous techniques to build upon to get this result. So what this result says is that we have to look at the distributions and decide, do we want to sell separately or do we want to bundle to a constant number of buyers? And if the distributions are regular, then selling items separately can be translated into actually selling items in a second price auction that is an auction that is independent of the distribution. So we can look at the distribution, either run a prior independent auction or bundle the items and sell them in some non-prior independent manner. But actually, when the distributions are regular, then we don't actually need to sell the items separately. We can just sell the grand bundle in a second price auction to a constant number of buyers and get 99% of the revenue. So actually, when the distributions are regular, the sum of them, which is the value of the grand bundle, is not necessarily regular. However, prior independent mechanism still achieves the type of results that we're looking for. So in the time that I have left, I'm going to talk about one of the results, the result that says that if we have a lot of competition, if the number of buyers is large, then selling items separately gets you 99% of the revenue. So I will be lying a little bit just to be able to go through the ideas of the proof. I hope this interests you, and if you want, you're welcome to ask me later more about the details. So the first thing that we need to do using the quartile decomposition is get an upper bound on the optimal revenue. And what we do is we get an upper bound that is separable across items. So whoever is familiar with the technique, usually it's separable across buyers. We had to do something a bit different to get separability across items. And now we get 4 terms for each item, and we have to upper bound each one of the terms up to 99%. So in the quartile decomposition, typically what we do is we separate the item values to small, to low, and high, using some thresholds, using some cutoff. And in our case, in the many buyer, many item case, since the values are coming from a distribution, this cutoff for each item implies a random bipartite graph of items and buyers. And we use this bipartite graph to analyze our upper bound. Specifically, we show that the contribution from the case where in a connected component we have 2 items is negligible, so we can throw this away into the 1%. And we set the cutoff in a way that in expectation, the number of buyers that have a high value for an item is a constant. Since the number of buyers is large, this also concentrates and happens with high probability, which means that if the number of buyers is far above this constant expectation, then again, this is a negligible contribution to the revenue, which means that we can kind of throw this away too. And now we're just, instead of having 4 terms, we just have 2 terms that we have to bound, and we have a nicer structure. And the other thing, the other component that we bring into the analysis is also accounting for the probability of sale in an optimal mechanism. So for each item, we can think of the optimal mechanism that we can't actually describe and ask, what is the probability of sale for this item? And remember this, and just write this on the side for now. And now, using this pi j, the probability of sale, the one term for each item is kind of like the low value, the contribution from the low values, times 1 minus the probability of sale. And since the number of buyers is large, we can 99% cover this term by selling items by selling to an epsilon fraction of the buyers with probability 1 minus this probability of sale. So one of the terms is covered by using a sale to an epsilon fraction of the buyers. The other term is kind of like the revenue from high values from a constant number of competing buyers. So we said before that the number of buyers in expectation that have high value for an item is a constant. And this translates to this second term that we bound, that is essentially kind of like looking at high values and the constant number of buyers, and we need to cover that. And to that, we use the remaining of the buyers, the 1 minus epsilon fraction of the remaining buyers, and we sell this item with probability kind of with the probability of the optimal mechanism. So using these 2 terms, this suggests the following mechanism, which is a selling separately mechanism that arbitrarily puts an epsilon fraction of buyers on the side and then says to the remaining buyers, I'm going to sell this for each item. I'm going to sell this item to you with a restricted probability from the optimal mechanism. And if you don't buy this item from me, then I'm going to go to the epsilon fraction of the buyers that I put on the side and offer this item to them and sell them in an optimal manner, that is like with a Meyerson mechanism. So this is a specific selling separately mechanism which gets 99% of the revenue. And since selling items separately and optimally is the benchmark that we're comparing to, then we get the result that we are looking for. Okay, so how much time more do I have? Okay, so I have 4 minutes. That's way more than I expected. So I can, now everybody who's not interested in this can go to sleep, and I will just talk to the people who are familiar with the literature. So what I'm going to do basically is just compare a few of our results to previous results and kind of like see where they're placed. So for example, do I have a laser here? So for example, this result, the n times log m over n, this basically says 99% of the revenue is upper bounded by selling items separately to n times log m over n of the buyers. So when the number of items is much larger than the number of buyers, comparing to our previous result from last year, this is an exponential improvement from O of m to O of n times log m, but we compare to 99% of the revenue instead of 100. So we get an exponential improvement, but to a different benchmark. Moreover, when the number of buyers is much larger than the number of items, the result that we were just talking about, we saw that selling items separately is 99% the right thing. And this is very similar to the result from Tsai and Huang from 2013, but instead of MHR distributions, for general distributions, and instead of n being a large constant in the previous work, like larger than a constant, here the term that matters is n over m, which has to grow. And the main challenge was going from MHR distributions to to arbitrary distributions. We also have the result of the second price for the grand bundle compares with the recent result by Kira and Anna that showed that if we have regular distributions, randomizing between selling items separately and selling the grand bundle gets a constant fraction of the optimal revenue. So what our result essentially says is that you don't need to sell the item separately. Selling only the grand bundle suffices. And finally, OK, and this I talked about before, so I'll end at this. And if you have any questions, thank you.
Questions?
So if I understood this correctly, the big assumptions are independence and additive.
Yes. Independence, and we're very strongly using independence not only across buyers, but also across items.
Right.
Both there. And of course, the additive assumption. And of course, rational bidders.
So, yeah, and so if you think of, those are pretty strong assumptions. You're getting amazing results, so it's not that surprising that the assumptions need to be very strong. But have you thought about trying to generalize to something that's, say, more consistent with a multi-unit auction? So where the independence and additive is, clearly ridiculous.
Yeah. No, everything is ridiculous about this model, of course, but in order to start from a point where you can get positive results, and then so for example, the result from last year holds also for more general than just additive. It's actually additive subject to constraints, so it's a bit more general. And one of the open questions is how can we generalize these types of results that very strongly rely on the additive nature of the valuations to more general valuation. And there is some hope that something will work because there are previous works that show for more general evaluations, a constant approximation is possible. For something that is called subadditive over independent items, you can show a constant approximation. So the hope is eventually these types of arguments and results will generalize to more general valuations, of course, and hopefully not necessarily independent distributions. Of course, you'd have to have some sort of restriction on the correlation because there are results that show that with correlation, essentially, there's almost nothing that you can do.
Any other questions? If not, thanks to all the speakers and the questions.